Okay. I feel like it's a recurring theme that I have to apologize. I don't have the exam graded yet. I think I set a record yesterday, though, because I walk into the office, and I really think it was about 7 seconds that the moment I set my bag down. I have a question, so because it's the registration season, so I would take the exam out, and then I'd have a question. And it was like that all day yesterday. So, but I only have one problem left. All in all, class is doing very well. If I had to guess an average, I'd probably say like class average is going to be like high 70s, you know. But I'm not there yet. So, but that's sort of like my gut feeling as to what the class average is going to be. So I think as a whole, class is doing very well. I'll come in on when I have the exam graded and do like I did last time. I'll put the solution up and we'll talk about it, and then we'll get into just get back to work. Okay, so today is a pretty important lecture in terms of setting the stage for flexural design of discretely braced beams. Remember, we said that discretely braced beams are the more general case, right? So a continuously braced beam is the same thing as a discretely braced beam with LB equals 0. So if you can analyze and or design a beam for an arbitrary LB value, then you can do it for a continuously braced beam since it just has a fixed LB value of 0. So we're going to discuss sort of that capacity model today. And so we'll set the stage for how that works and take our time with the LTB model and the spec, because it is a little involved. It's not terribly challenging, but you just got to take your time and digest it and whatnot. Did everybody get the code? Everybody get the QR code? Okay.
No.
That was good. I'm gonna give you credit for that one.
Thank you.
So, like my hand was going to the mouse, and it was just no.
I put a little jog in my step to get there.
All right. Okay. So, all right. So we're going to set the stage with LTB, but before we do, I want to go back to what we know so far about LTB. My little equations were supposed to turn on, so they're just, I'll just turn these all on all at once. Okay. All right. So what do we know so far about LTB? Okay, what do we know so far about this buckling capacity? Okay, so the first thing that we know is that a beam's maximum flexural capacity, or in other words, the maximum capacity that we can feasibly count on in a capacity setting is MP. Okay, so if I were to plot the capacity as a function of LB, right? So on the x-axis we'll plot the LB, right? And on the y-axis we'll plot MN, okay? We know a couple things. We know that right here at LB equals 0, we know that this term is MP, which is just Fy Zx. We know that, okay? We also know, so this first bullet where I'm saying that we know that a beam's maximum flexural capacity is MP, that means that whatever this picture looks like that's sort of our ceiling. We can't get higher than MP. Does that make sense? Okay, so that's the first point that we know. The second point that we should mention is that we do have an elastic solution for lateral torsional buckling. Okay, so this elastic solution was what we derived in class on Monday. Okay, now I'm being very prescriptive here when I use the term elastic. We assumed elastic behavior when we derived that solution, and we got this equation. So that should stand to reason, is there an inelastic solution? And spoiler alert, yes there is, and we'll get to that here in a bit. But this is also at least instructive to kind of, wrap our head around what we've got so far with our model, because we notice that in the expression, so here's our equation. LB shows up twice, and it's in the denominator. Okay, it's in the denominator outside the square root, and it's in the denominator inside the square root. So essentially what that means is that as LB gets bigger and bigger and bigger, what's going to happen to the moment that causes buckling? going to go down, right? So if we were to try and pictorialize that, maybe in some sort of generic plot, this plot should sort of be going like this, like in this general direction, that as LB gets bigger, the capacity goes down. We don't quite yet know what it looks like, but that's kind of what it should be doing. The other thing we now have is we now have this term C sub B, okay? So what is C sub B? Well, C sub B is an adjustment factor for this solution, because there was a problem when we derived this solution. Remember, when we derived it, we were assuming that M was a constant. M is not a constant in most practical applications. So we correct this solution with CB. Now, as we saw in our previous lecture, CB tends to be larger than 1. So actually what CB does is it sort of amplifies your capacity. It makes the capacity bigger, okay? So a couple things about that. First off, look, if we just look at the math, okay? So again, our LTB solution assumes M is constant. So if M is constant, this is our answer, okay? Now I propose that the actual answer we're going to use is this times CB. Okay, so what happens to CB if M is a constant? Okay, well, if M is a constant, within an unbraced segment, MA, MB, MC, and Mmax are all going to be the same term. So we'll call them M. So we have 12.5 M divided by 2.5, 3, 4, 3. So 12.5 over 12.5 is 1, right? So if the moment is constant, CB is 1, and I'm effectively taking this solution and multiplying it by 1, so I'm not changing it, right? So does CB still work if the moment is constant? Yes. Okay? Now, what I propose is that C sub B for any unbraced segment is either going to be equal to 1 or it's going to be greater than 1 based on the configuration of the expression. So actually what CB does is it tends to increase your capacity. Now, sometimes that's a little bit of an odd pill to swallow, I guess you could say, because you're basically wait, Dr. Mike, you want us to calculate this factor that you know is going to make the capacity higher? Isn't that unconservative? Like, shouldn't we just always take CB to be 1? The answer is no, because CB is intending to adjust your solution to reflect reality. So think of it this way. If CB is 1, what that means is that every segment along the cross-section experiences the same moment, okay? So if that's the case, then every single fiber of the cross-section is expected to reach its full strength before it buckles, okay? But that's not really how beams work. I mean, really how beams work, for example, is I have a simply supported beam, I got a load right in the middle, I only need to reach the maximum capacity right there in the middle, okay? I don't need to reach it everywhere else. Like the moments out here are pretty tiny, okay? So CB adjusts that to reflect reality a little bit. So that's why we use it. Okay, does that make sense? All right, so this is what we know so far about beam buckling, okay? Now I want to go back to a discussion on column buckling because I want to see if we can remember some analogies, okay? So if we go back to column buckling, remember we had derived this FE term, but we didn't just use it. The reason that we didn't just use it is because there were reasons why real column behavior deviated from ideal column behavior, the geometric imperfections and the residual stresses. I have that term residual stresses bolded here because residual stresses are going to have a big impact on beam buckling, which we're going to see here in a bit. But maybe what's also more apparent is that if you remember in column buckling, we had 2 zones. We had an inelastic buckling zone and we had an elastic buckling zone. So the idea is that what you would do is you would go along your x-axis and you would say, okay, here's my slenderness, my KL over R. I'm using LC over R to try and make this analogous to LB over here. But we would have a slenderness and we would compare it against this term, this anchor point, and we would say, all right, if my slenderness is over here, then I'm in this inelastic buckling zone. And if it's over here, I'm in this elastic buckling zone. And depending upon what zone you're in, I would get a different equation to compute my nominal stress. And then I would take that nominal stress, multiply it by the area, multiply by 0.9 to get the axial capacity, or the design axial capacity. Does that make sense? So we have these 2 zones that were determined based on whether or not my term lied along this anchor point. Okay, I mention that because I think now we've got enough discussion or enough stuff in our head to start talking about buckling of beams. Okay, so a couple things I'll say is that in columns we had 2 zones of buckling, or 2 zones of capacity, either inelastic buckling or elastic buckling. And in the case of beams, we have 3 zones. Okay, and you'll see those here in a bit. And they're going to, so if there's 3 zones, there's going to be 2 anchor points that separates those. So there's going to be like an anchor point right here and an anchor point right here, and we're either in zone 1, zone 2, and zone 3. Okay, and there's these 2 anchor points, and so we'll need to determine those and figure out what zone we're in. And I also want to highlight how CB actually affects the capacity and how we can take this little generalized schematic here on the board and add some reality to it. Okay. All right, so let's look at the beam capacity specifications. All right, so like I said, there are 3 zones, okay? Those zones are going to be split up by anchor points, and we have names for those anchor points. We call those anchor points LP and LR, okay? So basically, for any analysis problem, what you're going to do is you're going to look at your LB and you're going to compare it against LP and LR and figure out whether you're in zone 1, zone 2, or zone 3, okay? So what are those zones? Okay, so zone 2 and zone 3 are sort of like the zones for column buckling. We have an inelastic buckling and we have an elastic buckling. Zone 1 is just straight up MP. Okay, so how do we compute the capacity in zone 1? It's just MP equals FYZX. How do we compute the capacity in zone 3? Zone 3 is that derived equation that we use. Okay. So what's zone 2? If we know what zone 1 is and we know what zone 3 is, what's zone 2? Zone 2 is just a straight line fit. And it's a straight line fit between not MP and MY. That would probably make sense to think, well, it's probably between the plastic moment and the yield moment. Instead, what it is it's between the plastic moment and this term MR. And MR is a reduced yield moment. Why is it reduced? It's reduced to account for residual stresses. Okay? Remember with columns, remember when you roll the column cools at different rates and it sort of sucks in that differential cooling set of strains. So part of the beam's in compression, part of the beam's in tension. That affects stability, and this is a stability problem, so we have to account for that. Okay, now I'm going to give you a nice little pretty picture of the LTB curve, okay? And then we're going to take this picture and we're going to break it down a little bit. So there's a lot going on here on the slide, so I want to sort of like digest it a little bit. Okay, so let's start here on the x-axis. Okay, so here on the x-axis, we're plotting our LB, right? Okay, so in general, as LB is getting bigger, the capacity is kind of trending downward, which we said was going to happen. Okay, well, in that's the case, that's happening here. Now, how do you figure out what zone you're in? You're either in zone 1, zone 2, zone 3, dependent upon where your LP and your LR is. So, like for example, if LP is 8 feet and LR is 15 feet, what you would do is you would look at your LB. So if LB is, say, 10 feet, that's zone 2. I mean, hopefully that's pretty straightforward. Okay. Now, what I want you to do for starters is focus on the solid line. Don't focus on this dash curve, because I'm going to talk about this dash curve here in a bit. Just ignore the dash curve. Let's focus on the solid line. Let's talk about zone 1. Zone 1, the capacity, I don't care where you are in zone 1, the capacity is just MP, just FYZX. That's all it is. Okay? What about zone 2? Zone 2 is just a linear interpolation. Okay? So we've got this point here, which is sort of like LP comma MP, this point right here, which is LR comma MR, and so dependent upon where your LB is, you just linearly interpolate. Okay? Now, I imagine everybody in here can linearly interpolate, so we don't need to go down the rabbit hole here, but one piece of notation that I'm going to throw at you is that the manual has a way of making this really easy by providing the slope of this line, and they call the slope of this line BF for beam factor. Okay? So what is BF? BF is just change in Y over change in X. Okay, so you'll see us look that up here in a little bit. Okay, now this term, or this zone 3 right here, that's the elastic buckling solution. Okay, that's what we derived on Monday. That's all this is. Okay, now, like I said, this is the solid curve. I do kind of want to explain this dash curve. So let me kind of show you this. I put a link to this, by the way, on Blackboard. So I have here, this is a Desmos plot. Is everybody here familiar with Desmos? So this is a Desmos plot, and this is Desmos for lateral torsional buckling, and I plotted this for a W24 by 76, okay? So just so you're aware, everything's in inches, right? So this is inches, and this is inch kips, okay? And so you can see I've got, this is LP, this is LR, okay? Now, I'll show you, you've got this solid curve and this dash curve. What's going on with the dash curve? Okay, so this dash curve reflects this CB term, okay? Now, if CB is 1, so if CB is 1, then the capacity isn't changed, right? In fact, the solid curve, or the dash curve is just the solid curve essentially times CB. But if CB is 1, then it doesn't change. But what happens, so what does CB do? CB tends to increase your capacity, okay? So I've got CB sort of animating right now. But notice what it's doing, okay? So what CB is doing is it's increasing the capacity, but it's cutting it off because it's saying, I really don't care what CB does to the curve. At the end of the day, the capacity is limited to this plateau because that plateau is MP. That's the highest capacity that we can account for, okay? Does that make sense? So at the end of the day, the maximum flexural capacity is MP. So when you look at your zone 2 and your zone 3 expressions, you're going to see some terms and you'll see how that's being accounted for, okay? Does that make sense? Okay. Okay. All right. So does everybody kind of get the picture, like the visual image of what we're talking about here? So now let's get into the math. And I want everybody to take a breath on this next slide because I have got an equation and a half on this next slide. That, I think, is the worst equation I have in, I think, really any of my classes, is the equation for LR. Because it's like a square root and then another square root. That's not a mistake. That is the longest equation, I think, in any of my lectures. Okay? Yeah, so this is the expression for LP and LR, okay? And so, first off, like I just want to be clear. Yeah, it's a long equation, but like for example, I have spreadsheets that I use where I have this equation, like I built it once, and then now I can just use it forever. So in the real world of engineering, like long equations really shouldn't scare you because you can Excelify those equations and never have to program them again. So don't let a long equation really alarm you. But we actually, in all honesty, are not going to have to use LP and LR because the manual just calculates them for us. So that makes life a little easier. One thing that is actually a little counterintuitive is that if you were to ask me which is the harder equation to derive, LP or LR, actually the more challenging equation is LP, okay? And I want to explain why. So LR, while it's kind of nasty, is really just the result of algebra. What you do is you take that differential equation solution that we came up with, set it equal to the reduced yield moment, 0.7, FYSX, and solve for the length. And yeah, it's kind of a nasty algebra problem, but at the end of the day, this is what you get. So you could actually, in a matter of a few minutes, derive LR. Is it fun? Well, it's alphabet soup of algebra, but you can do it. This one's a little bit more challenging because it requires a lot of experimental testing, maybe a lot of computer modeling and whatnot to sort of try and come up with a reasonable point at which you say buckling starts to occur. And it's not simple. It requires judgment and it requires a lot of testing and whatnot. So there's a lot more work that goes into this than you would think. Maybe that's one of the reasons why the expression's so easy. Okay. All right. So that's LP and LR. So how do we calculate our capacities? Well, zone 1, I don't have a slide on zone 1 because the capacity is just empty. It's just FYCX. So what about zone 2? Okay, so I have two equations here, and I want to be clear as to what I mean here. So this equation right here, this one up top, is what you get right out of chapter F. So if you open up the spec, go to chapter F, okay? That's the equation that's going to be listed in chapter F, okay? That's not the one we're going to use, though. What we're going to use is this, okay? So let me walk you through how I get from here to here, okay? So first off, zone 2 is just linear interpolation, okay? So this, MP minus 0.7 FYSX, this LR minus LP, that fraction is just the slope of that linear line, right? So I'm taking this all this hullabaloo and replacing it with BF. So I'm going to make that part a little bit easier, okay? So that's step 1. Step 2, remember when remember we started looking at expressions like this in the manual and we said, okay, whenever you have a capacity equals a pile of junk such that it's less than or equal to another pile of junk, really what we're saying is it's the minimum of those two quantities. So we do that. And then the third thing we do is we incorporate our phi values, okay? So what I'm saying is I'm saying the capacity, this and this are the same thing, just rewritten a little bit in a manner that's a little bit more easy to use. So I'm saying phi mn equals the minimum of this, okay? So it's either this hullabaloo or phi mp. So I'm saying the capacity is either the minimum of what you calculate or mp. So the reason why we have the minimum is, remember the curve as I was animating it, it was cutting it off at mp. So what this is saying is, I don't care what you calculated, we're cutting it off here. That's what that's saying there. All right, yes?
And you're saying VF is just a lookup once you pick the shape to analyze?
Yes. Yes. Okay. I'm going to show you that here in a second. Okay, now zone 3. Zone 3, unfortunately, there's not like a shortcut with zone 3. I would like it if there was some way of like shortcutting this, but there isn't really. We just kind of have to chug our way through it. Okay, so that's our expression. Now, a couple things about this. Okay. So the way zone 3 works is the first thing that you do is you compute an F critical, which is this term, and then the actual capacity is the minimum of phi F critical SX or the plastic moment. Okay? So a couple things about this. Number one, this is the same thing that we derived. It's actually the same expression that we derived in the differential equation, but if you go back a few slides, like here's this, okay, and if I go back a few slides to this, like they don't look the same. They look different. So a question might be, well, wait a minute, Dr. Mike, why does this equation look differently? Like what's the whole, why make the equation look differently? Why are you making this complicated? The answer is the manual is actually trying to do you a favor and not make things complicated. So a little background. What I am presenting right now, this is the differential equation solution for LTB, assuming that the shape is doubly symmetric. And what I mean by doubly symmetric, it means we have an I-shaped cross-section where the top flange and the bottom flange are the same flange, same shape, right? Which for a W section, of course, it's literally the same shape. But in bridge land, that may very well not be the case. It is very common in bridges that you'll have a top flange and a bottom flange that have different shapes. Okay? So what I'm saying is in bridge land, what we derived isn't going to work. Okay? So the question is, what is going to work? Well, there's a different solution. The singly symmetric solution, for lack of a specific statement, I'll say, looks a lot like this. Okay, so the idea is that this equation has been reformatted so that the singly symmetric solution and the doubly symmetric solution have a lot of the same characteristics and a lot of the same quantities to make your life a little easier when navigating the spec. So again, it's the spec's way of trying to do you a favor, not trying to make things more complicated. So, but that's why it's reformatted. Okay, couple things. So what goes in here? What goes into this expression? Well, we need CB, which, we've talked about that. We need an E value, which is 29,000 KSI. There is a term C that shows up, but it's just 1 for I-shapes. It has a computed value for channels. And then what else do you need? You need an RTS, you need a J, an SX, an HO. All these properties you can look up. So it's really just a plug and chug. The only thing I'll say is be careful with the LB value, because you're taking LB and dividing it by this, so it needs to be in inches. Okay, so just throwing that out there. All right, so far so good? Okay, so I threw a lot of terms at you, but I actually want to go back to table 3 too, because remember what I said? I said by the time this semester's over, you'll know what every one of these terms are. Well, what do we have here? All we've looked at is these two and then this over here. Well, look, we got a FEMR, we have a FEBF, we have an LP and an LR. They're all there. So if you look at shape up in table 3 too, a lot of those base capacity or base values for the LTV capacity, a lot of that work's been done for us. We don't have to compute FEBF. We don't have to compute this. We don't have to compute that. They're all listed. Okay? Does that make sense? Okay. Now, if there was ever an Instagram-worthy slide, it would be this one. Okay? So I really tried to make this sort of neat and tidy. Like, so the idea is that what I'm doing here is I'm taking I'm taking that plot and I'm sort of flow charting it. So the idea is that if you're in zone 1, this is the capacity. If you're in zone 2, this is the capacity. If you're in zone 3, this is the capacity. So I'm just, here it is, all in one. Hey, here it is. Okay? Sound good? Let's do an example. Okay? So we're going to go through a couple of design aids today in the manual. So I'm going to give you all a sec to write this down, but I'm going to say a few words about it while you're writing. So I have here a W24 by 76, okay? And we're going to determine whether or not this has adequate moment capacity, adequate shear capacity, and we're going to determine whether or not it meets a live load deflection limit of L over 360. Now, first off, I don't care if this is a continuously braced beam. I don't care if it's a discretely braced beam. The L over 360 step, that's the same. We're still doing, our deflection check, the same as we did before. That doesn't change. Okay. The capacity calculation, though, that is going to be different. Okay. So let's see what we can do with this. All right. All right, let's see. All right, first thing I want to talk about is this little note right here. Okay, so let me read this out. So it says, since the beam is symmetric with respect to the loading, geometry, and bracing, only one segment will need to be evaluated for moment capacity. So what do I mean by that? Okay. Let's discuss that a little bit. What is the moment diagram going to look like for this beam? Your other way. It's going to go like that, right? Am I right? Okay. So how many unbraced segments do we have in the beam total? How many unbraced segments do we have? 2. There's 2 segments. There's the one on the left and the one on the right. Okay? So what is the LB term for those segments? 15 feet. Okay. So what I want you to start thinking of when you're assessing strength, like if you're trying to determine which segment governs, I want you to look at CB, LB, and MU. So let's sort of consider these terms. Okay, so for both segments, would you agree that LB is 15 feet? Do you agree with that? Okay. Now, let's talk about CB and MU. Okay, so let's just conceptualize this. How would we compute CB? So would that be M max for both segment? That's going to be the maximum moment. This right here is going to be M max. Is that fair? So remind me, so let's take the left segment. How would we compute CB? What do we do? This is M max. What else do I need to compute CB?
Another 0.75 feet.
And that's going to be what?
MA.
No. Oh, okay. Let's talk about this. All right. This is the segment. Okay. This from here to here is the segment. So quarter point moments within this segment are going to be bam, bam, bam. That would change if this brace wasn't here. Then it would be MA, MB, MC. Okay, does that make sense? So within each segment, I'm going to say MA, MB, MC, right? Okay. But aren't I also going to have to do that over here? So if this is MA, if this is MB, this is MC, right? Isn't that going to be the same thing over here? All right. So you're telling me LB is the same for both segments. What else can you tell me is the same for both segments? CB is the same for both segments. What can you also tell me? Isn't the maximum moment the same for both segments? So what I'm getting at is in order to determine whether or not the beam has adequate moment capacity, I only need to look at one segment. I don't need to look at both of them. They're literally the same. Okay? Does that make sense? That's not always the case, mind you. Okay? And we're going to talk about some examples of that later. But there you go. Just want to throw that out there. Okay. Now, I want to show you something. I am lazy, as I've mentioned a number of times before. And so I really don't like doing more math than I need to. This is a simply supported beam subjected to a uniformly distributed load. So I'm going to go here to my little manual guide here. Okay. I'm going to go here. I'm going to go to part 3. All right. Y'all know where the ZX table is, right? Turn one page prior, and we get table 3.1. Table 3.1 on page 3-18, values of CB for simply supported beams. A simply supported beam subjected to a uniformly distributed load is about the easiest case that you could deal with. Okay? Now I want to show you how to navigate this table a little bit. So let's take a look at these first two cases. This ain't going to apply for our problem, but let's just take a look at these first two. So I have this right here, simply supported beam with a load at midspan. Okay? What this is saying is if I don't have a brace at midspan, CB is 1.32, but if I do, CB is 1.67. So it went ahead and computed the CB for us. Okay? So what I'm going to do is scroll down and I ask you, what is the CB going to be for our problem? 1.30. Okay, does that make sense? So if you want to compute CB, you're more than welcome to. In fact, I gave you a homework assignment where I am sort of making you do that. But if you don't have to, don't do it. All right? Make sense? Okay. All right. Okay. So now that we've gotten that out of the way, let's go to table 3.2 and look up a W24 by 76. Okay? So here's the manual. I'm going to flip the pages over a little bit. Okay. W24 by 76. Okay. Now, if I'm trying to, okay, so let's figure this out. Okay. I need to. My goal is to try and determine the capacity. I want to know the flexural capacity of the beam. Now, I already know what the shear capacity is. It's just 315. What about the moment capacity? How do I figure out what the moment capacity is based on this flow chart? What do I need to look up first? Well, let me ask it this way. Do we all agree that flexural capacity is a function of what zone we're in? How do we determine what zone we're in? LB compared against what? LP and LR. So for a W24 by 76, here's LP, here's LR. Okay, does everybody see that? So we have a beam such that LP is 6.78 feet and LR is 19.5 feet. Okay, so that comes from table 3.2. Okay, now for our beam, is 15 feet. What does that tell you? Zone 2. And if you wonder why I stick a line through the middle of my Z's, this is why. Because that's a Z, that's a 2. I promise they're different symbols. Okay, so would it makes sense that we're in zone 2, right? Is everybody okay with that? So the first thing that we need to do is we need to compare our LB against these two terms to figure out what zone we're in. Okay? So if that's the case, here's our little flow chart. Okay? So we're definitely here because our LB is between LP and LR. And if that is the case, I propose that our capacity is going to be governed by this expression. Okay, so this is how we're going to compute the capacity. All right. So let's go through what's inside here. Okay, so let's go through what's inside here. CB, we have our CB value. All right, let's see what else. What do we got? Phi and P. What is Phi and P? What is Phi and P? And where do we get that? We just look it up, right? Just straight look it up from table 3.2. Right? So all I'm doing is I'm going back here and I'm saying, all right, I need Phi and P. I need that. Okay, what else do we need? We need Phi BF. So Phi BF is what? 22.6. And it's 22.6 kips because you take kips, multiply it by distance to get foot kips. We need an LB of 15 feet. An LP of 6.78 feet. That's what we need for this computation. Okay? Does that make sense? Okay. So the way that I like to do this, at least when I'm doing it in class, is so the first thing I'm going to do is I'm just going to compute all this hullabaloo on the top row. This is whatchamacallit. All right, so this is CB times Phi B MPX minus Phi B BF LB minus LP. Why is that term negative? Why is this term negative right there? Why is that negative?
The slope of the graph is negative.
There you go, because it's going down. Let's make sure everybody's awake. Okay, so this is 1.30 times 750 minus 22.6 and then 15 foot minus 6.78 foot. See, notice the manual's done a lot. I mean, if you go back to the original expression in the spec, and then go to this, the manual's really done a lot of work to compress this calculation, make it easy for you. They're really trying to do you a favor here. So, what do we get for this?
733.5.
733.5. Do I have a second? Move this down just a little bit. Okay? So this was this first line, but that's not technically the capacity. Okay? Because the capacity, this is how I like to write it because I'm kind of lazy. The capacity equals the minimum of CB times all that nonsense, or phi and P. Okay? So this top row is just this. I'm just kind of lazy and doing that. So this is the minimum. You get all these sound effects in my class. The minimum of 733.5 foot kips over 750, right? And by the way, what is our capacity, or in this case, going to be? Okay. Okay. I would argue from this point moving forward, this is no different than any of the other beam analysis problems that we've done. Okay? But is everybody with me so far? I want to take one slight deviation, and I want to go to this. Okay? It's almost like I had a plan here, because this curve is, what's this curve? A W24 by 76? And what was our CB value? 1.3? So okay, so here's what's going on. Our LB is 15 foot, and I'm sorry, I have this in inches. What's 15 times 12? 180. So if I go to 180, what's happening is if I go to 180 and I go up, so this is the curve. So my capacity is right here, and look what's happening. So would you agree that my, whoa, moving the mouse, would you agree my capacity is about right there? Would that make sense? So the capacity is like, it's close to MP, but it's not quite there. You know, it's kind of close. And what did we get in our math? We got that, I mean, it's kind of close, but it's not quite there, right? So I'm just trying to paint the whole picture, okay? Make sense? Okay. From here on out, I'm going to do this problem pretty quickly, but it should be pretty familiar, okay? So I want to make sure that what I've done so far, that this is the part that makes sense. Everybody good with me on this? Yes?
I just have a question. For the phi PF, do I need to make a slope calculation or just look?
I'm saying this is the slope. So what I'm saying is, okay, here's how I would answer that. Okay, so let me erase all my annotations here. So here's what I'm saying. So we agree here's the 24 by 76, right? Okay, what I'm saying is that you've got, here's LP and LR, right?
Yeah.
So that's going to be the change in X, like the difference between the two, right? And then I propose that this and that is going to be the change in Y. Take the difference of these two, and divide them. You'll get that. It's doing it for you. That's what I'm saying. So you're already doing the slope when you use BF. So that's a fair question, though. But this is a way of checking it. So it's good stuff. Any questions? Okay. All right, so past this, like I said, I'm going to go through this kind of quickly, but I'm hoping that you'll kind of see what I mean, because it's, you know, at this point it's pretty straightforward. Now, here's the problem. Okay? And we're told that W sub D is 1.25 kips per foot, and that this includes self-weight, so we don't need to add the extra 76 pounds per foot for the W24 by 76. It's built into this. There's that. Okay, so, and we know that this is 30 feet. We can go ahead and write that this distance is 15 feet. But for the purposes of structural analysis, the braces don't really affect the computation of moments. Okay, so what we're going to have is we're going to have a VD of WDL over 2 and an MD of WDL squared over 8. And when you chug these out, you're going to get 18.75 kips. This is going to be 140.6 foot kips. And then, same thing with the live load. This is 45 kips. So we have our dead load and our live load. Okay. So for moments, so if we do moments, we get 1.2 moment dead plus 1.6 times the live load moment, and we get an MU of 708.75 foot kips. By the way, what was FMN again? What did we calculate? What does that mean? We are good. That performance ratio, by the way, is 0.966. When we do shear, we get a shear of 94.5. And remember, we were able to look up the shear capacity. And the shear capacity is 315 kips. So are we good here? Of course we are. That performance ratio is 0.3. Okay. And lastly, what I'll say for the deflections is that we're going to calculate it using this. And what I'll go ahead and put the 1728. Again, is it okay if I just chug through this? I'm hoping you all can do this one at this point. This is 0.898 inches. And then our limit, again, for this problem was L over 360, which is 1 inch. Because it's 30 foot long, 30 foot's 360 inches, so if it's L over 360, it can't deflect more than an inch. And it's deflecting 0.898. So are we good here? Yeah. And that performance ratio is really easy to compute. Pretty straightforward. Again, like really the only difference between a discretely braced beam and a continuously braced beam is how you compute the capacity, the flexural capacity. Once you get past that, it's no different. It's the same problem. So, sound good? All right. I will see you all on Friday. That's all I got, everybody.